let us start once more. So to briefly recapitulate what you have probably missed is that I try to make a short summary of the last lecture. So I remind you that there were right-handed and left-handed spinors transforming according to this representation of the Lorentz group, and also that we obtained an infinite dimensional representation of the Lorentz group acting on field in two ways. Either the active representation, when we have some configuration psi x acted on this by such an operator, and we obtain the transformed configuration in the same point. That means we have two different field configurations which are connected by the Lorentz transformation, and also passive interpretation when we interpreted this simultaneous transformation of the coordinates and of the fields, assuming that this first corresponds to the description of the transformation of coordinates of the same space-time point, and this corresponds to the transformation of the values of the fields at the same space-time point, now described by different coordinates x prime and x, which are connected with the Lorentz transformation. We have also introduced some spin vectors, some matrices, 2x2 matrices, which obey such relations. And we have found that using the matrices of the left or right spinor representation, we got such relations which allowed us to construct from two left spinors something which transforms like 4-vector, and in the same way two right spinors we obtain something which transforms like the 4-vector. And since the transformation of the derivative is according to this formula, we can obtain invariance. For instance, taking such an object. Now let us have only one right-handed spinor, and if we form such an object, this object is invariant. Simply because under the Lorentz transformation, the right-handed and right-handed spinors transforms according to the relation psi r u r cross sigma, and the derivative transforms as sigma mu lambda mu d. So if we calculate the transformation of this psi r, but this psi r also transforms by the right-handed matrix ur, and we see that we can use this first relation to obtain that the result is just lambda mu, sigma mu beta lambda mu alpha lambda mu beta times psi r cross sigma alpha b beta psi index r. And since these matrices are inverse to each other, we obtain as a result simply delta alpha beta. So we again reproduce the original expression psi r sigma times derivative of psi r. So we know how to contract the vectors, derivatives, in order to obtain invariant. And such an invariant is nothing else but the kinetic term for the right-handed spinors. We will return to this later. There are also several useful relations which allows us to form all those scalars directly from the spinors. For instance, if I show you again this relation defining the left and right representation, we immediately see that if we calculate the Hermitian conjugation of this matrix, that means the Hermitian conjugation of such an exponential parametrization of the corresponding UR and UL matrices, we obtain, since this phi and u are real vectors, minus plus, since here is imaginary unit, and comparing it with the original expression for this UR, UL matrices, we see that this is nothing else but, UL, or right to the -1, inverse matrix. Simply here changes the sign, and again here the sign is changed. So we have such a useful relation, and this allows us to form scalars from left and right spinors. For instance, taking right spinor, Hermitian conjugated, by combining it with left spinor. Transformation of this is just psi r UR cross times UL UL, but using this relation we obtain psi r cross UL inverse UL psi L, nothing else by psi r cross psi L. So this is scalar, this is invariant. Some question? Okay, similarly we can use another invariant, psi r cross psi r, in the same way. But we can also form invariants from left spinors and right spinors only. The key observation is the relation which we can write in such a way that we sandwich the transpose of the Pauli matrices with Pauli matrix sigma 2. And the result is just minus sigma. This can be proved by direct calculation. Simply this sigma 2 anticommutes with sigma 1 and sigma 3, and sigma 1 and sigma 3 are symmetric matrices. So the anticommutation of these matrices gives just minus sign here, and sigma 2 times sigma 2 is just 1. So left-hand side for sigma 2 is just sigma 2 transposed, and sigma 2 is anti-symmetric. So again, we get this minus sign here. And this is a very useful relation, since we now can try to calculate such a sandwiching of U, R, of L transposed and relate it to the U, R, and L. So using the definition of this URL, we obtain just exponential of half sigma times this phi plus minus I U. And this should be transposed, and the transposition here means, in fact, transposition of this sigma matrices. And expanding this exponential in power series and using this relation, it is easily seen that this can be also rewritten as such a expression. And using again this magic equation, we here obtain exponential of minus I half sigma times phi plus minus I U. And comparing this with the original UR and L, we see that this is nothing else but the URL to the -1, since here is minus sign. So if we have two spinors which are left-handed, psi 1 L, psi 2 L, we can form from these spinors again invariant, simply writing psi R L1 transpose times this sigma 2 times psi R L2. Since if we transform this, what we obtain? Sigma 1 transforms as L representation, but it is transposed, so we should write it like this. Then we have sigma 2 and psi 2 was L. But we can insert here 1 in the form of sigma 2 squared. And what we get is sigma 1 transposed sigma 2 times sigma 2 ul lambda transpose sigma 2 times psi L2. And according to our previous derivation, this is just, sorry, I forgot, of course, to transform here also this left-handed spinner again here. So this is nothing else but ul inverse, and this is cancelled by this ul. So we see that this is just the original expression, sigma 1 transposed sigma 2 sigma 2 psi 2 left. So sorry. So again, this is invariant. And in the same way, we can also form analogous invariant from the right-handed spinners. But of course, since sigma 2 is anti-symmetric matrix, it is necessary to have psi 1 are different from psi 2 unless the invariant is 0. We can rewrite this formula also in another way, using the fact that these sigmas are Hermitian. So sigma t is sigma star, the complex conjugated. So we can obtain a similar relation with complex conjugated sigma matrices. And this can be used to show that in fact there are no other two-dimensional representations beyond the left-handed and right-handed spinners. Of course, you can argue that if I have representation d0 1/2, I have also a representation d0 1/2 complex conjugated. Simply corresponding matrices are complex conjugated of the right-handed matrices. And again, it is representation. Analogously, if I have left-handed representation, I can form the complex conjugated left-handed representation, which corresponds to complex conjugated left-handed matrices. So let us show that in fact this complex conjugated right representation is equivalent to the left representation and vice versa. So let us use the same, that sigma 2 inverse is just sigma 2 because square of sigma 2 is just 1. So we can write sigma 2 to the -1. You say R or L complex conjugated sigma 2. And what we get? We get sigma 2 times exponential of I/2 sigma times is phi plus minus I u complex conjugated sigma 2. And this is nothing else but exponential. First, we should make complex conjugation. So we change the signs, and then we insert this sigma 2 in the exponential, as I have explained before. So what we get is just exponential of minus I/2 sigma 2 sigma complex conjugated sigma 2, and now phi minus plus I u. But this is nothing else but minus sigma. So we see that this is in fact either left-handed if we take upper sign here, or right-handed if we take lower sign here, representation of the Lorentz group. So we see that there exists a similarity transformation between the complex conjugated right or left-handed matrices and the left and right-handed matrices. That means then, in fact, this complex conjugated right-handed representation is equivalent to the left-handed representation, and the left-handed representation, complex conjugated, is equivalent to the right-handed representation. Simply, we need only to make some arrangement of the coordinates in the corresponding complex conjugated representation space, and we can write the corresponding matrices in new coordinates as left-handed representation and right-handed representation. So in all formulas for the vectors, scalars we have so far, we can simply exchange the left-handed spinor by sigma 2 times the right-handed spinor complex conjugated, and vice versa, the right-handed spinor we can replace by sigma 2 times left-handed spinor complex conjugated. And all the formulas for the invariants will be again invariant. So to conclude, from the left-handed and right-handed representation, we are able to obtain scalars, vectors, other scalars, and in all these formulas, we can use this replacement of the left-handed or right-handed spinors without changing the nature of these objects, of these billinars in the spinors. Again, are scalars, vectors, or scalars. Now, we know that another important representation which will be connected, for instance, with the Dirac equation, are the representation d1/2 0 plus d0 1/2, which we called the Dirac bispinors. Such a Dirac bispinor is therefore in block form, can be written as psi r and psi l, where this psi r is right-handed spinor and this psi l is left-handed spinor. And again, in this representation, we can form from this Dirac bispinors various other objects with obvious transformation properties with respect to the Lorentz group, namely the scalars, vectors, and so on. And even we can form also objects which have definite parity. So we can form, for instance, proper vectors or axial vectors or scalars or pseudoscalars. In order to have a corresponding machinery, let us define some 4x4 matrices, which will be useful for us. As a first such a matrix, let us define a matrix called gamma 5. And the definition of this gamma 5 matrix is just this. So we see that this matrix is Hermitian, and the square of this matrix is just 1. And from this gamma 5, we can form the right or left projector, simply taking 1 plus minus gamma 5 over 2. And these objects are really projectors. That means they are Hermitian. And the square of such a projector reproduces it. And these projectors are orthogonal to each other. That means the left projector times the right projector is the same as the right projector times the left projector. The result of such a multiplication is 0. Of course, we see that such projectors project to the first or to the second component of this Dirac bispinor. Another matrix which will be interesting for us is called gamma 0 matrix. And this is defined again in 2x2 blocks as such a 4x4 matrix. Again, this matrix is Hermitian and its squared is just unit matrix. And using this matrix gamma 0 and gamma 5, we can construct two types of invariants of the proper orthogonal Lorentz group. Namely, if we define the so-called Dirac conjugated spinor simply as psi bar, this is the 4-component column, which is defined just as psi cross the Hermitian conjugation times gamma 0, we can then form the following invariant. Psi bar, say we have two such spinors, psi 1 times psi 2, psi 1 bar times psi 2. What is it? So in components, this can be written as psi r cross psi l cross times this matrix gamma 0, which is just the permutation matrix, which when it acts from the right, it simply changes the corresponding R and L components. So we get here psi L cross and here psi R cross. So calculating this, we obtain just psi L1 cross psi R1 cross times a column psi 2 R psi 2 L, and simply the result is psi L cross psi 1 L cross times psi 2 R, and we already know that this is invariant, plus analogously psi R2 cross psi L 1 psi L2, and this is also invariant. So this is one type of the invariance, and we will see that this is the proper scalar. And we can also form pseudoscalar, simply taking just this gamma 5 and forming such a bar. So what we get here, again, this psi 1 bar can be written as psi 1 L cross psi 1 R cross. But now the matrix we are interested in is 1 minus 1. So we get just, here is psi 2, right, psi 2 L. And we see that we get just similar invariant as in previous case, but with minus sign between these two terms. So we obtain psi 1 cross L psi 2 R minus psi 1 cross L psi L2. In order to decide whether this is scalar or pseudoscalar, we should represent not only the elements of the proper orthogonal Lorentz group, but we need also the operator of parity or the special inversion. That means we need representation of L upwards orthogonal Lorentz group, which is just unifying of these two components of the Lorentz group. We will return to this later. Now, what about forming vectors, Dirac spinors? Of course, we can do something like this. Take Dirac spinor 1, Hermitian conjugated, and let us take such a matrix, sigma mu 0, 0, sigma mu bar times psi 2. So if we again, this psi I is column by two components, the right-handed component and left-handed component, we see that this is just sum of the two vectors which we have formed from left-handed spinors and right-handed spinors, simply psi 1 R cross sigma psi 2 R plus psi 1 cross R sigma bar psi R2. We can also rewrite this left-hand side in terms of the Dirac conjugated spinor. So in order to reproduce this, we should multiply the Dirac conjugated spinor from the left by gamma 0, since gamma 0 squared. 1 and psi bar is psi cross times gamma 0. And again, we get here sigma mu 0, 0, sigma bar mu times psi 2. And if we calculate this, I remind you that this sigma 0 is just such a block permutation matrix. So we obtain the following. And these matrices are in this context called the Dirac gamma mu matrices. Therefore, gamma mu is just 0, sigma bar mu, sigma mu, in terms of 2 by 2 blocks. So there is possibility to construct vector from Dirac spinors, simply psi1 bar times gamma mu psi 2. And similarly, we can construct also axial vector or pseudo vector using just this construction, gamma mu, and the matrix gamma 5, which we already used. And if we do all the matrix multiplication, we see that the only difference is again the minus sign instead of plus in between these two vectors. So these gamma matrices are useful in order to form the vectors and axial vectors from the Dirac spinors, but they have a lot of very important properties for us. Namely, if we calculate their anti-commutator, so we calculate 0 sigma bar mu 0 times 0 sigma bar mu 0 minus mu, plus mu interchange by mu, what we get. So doing this calculation, we get just first row times first column. That means sigma mu bar sigma mu. First row times second column 0, second row times first column 0, and here we obtain sigma mu sigma bar mu, and plus mu interchange with mu. And since we know the relation, for instance, sigma mu plus sigma mu is twice eta mu, and analogous sigma bar mu plus sigma bar mu is twice eta mu, we see that we get so-called Dirac algebra gamma mu of these 4 by 4 matrices, which is 2 eta mu. Sometimes it is also called Clifford algebra of the group SO. And why this Clifford algebra is so important? For instance, if we form from these matrices new matrices sigma mu, which are defined as I half gamma nu commutator, it can be easily shown, and I leave it to exercise as an exercise for you, that the objects capital sigma mu, which is minus 1/2, this smaller sigma mu, it is just the notation. We could start with this capital sigma mu, but usually everything is expressed in terms of this small sigma mu. And these capital sigma mu obey the algebra of the generators of the Lorentz group. That means sigma mu commutator sigma alpha beta is just I eta mu alpha sigma mu beta plus minus these alternating terms. So this is the algebra of generators of Lorentz group. So we can represent the general element lambda omega of the Lorentz group just with these sigmas. So we can represent it as exponential of minus I over 4, the small sigma, omega mu times the small sigma mu. And it is another exercise just to find that this sigma mu matrices looks like I over half minus I over 4th sigma bar mu sigma mu minus sigma bar mu sigma mu, and sigma mu sigma bar mu minus sigma mu sigma bar mu. And if you calculate this, you find that the generators corresponding to rotations are now represented as 1/4 plus epsilon ijk corresponding sigma jk. Normally it was minus 1/2 epsilon ijk jk, and these jk are now represented by minus 1/2 these sigma jk. And if you calculate this, you find that this is nothing else but 1/2 sigma I, 0, 0, and 1/2 sigma I. That means this is just the generator of the right-handed rotations. This is the generator of the left-handed rotations. And similarly, the generators of boosts are now just minus 1/2 sigma I, 0. And if you calculate this, you obtain just I over 2, and here is sigma I, 0, 0, and minus sigma I. And these are just generator of the boost in the right-handed representation. This is just the generator of the boost in the left-handed representation. Why are these gamma matrices connected with Dirac equation? Simply because you can form the alpha matrices which enters the Dirac equation simply by multiplying the gamma I matrices with I 1, 2, 3 by the matrix gamma 0 from the left. And if we define the beta matrix as just the gamma 0, we obtain the usual algebra of the alpha and beta matrices in the Dirac equation, which can be written in the form I time derivative of the psi. It is minus I alpha times gradient plus beta m psi. I have promised you that I will show you that this Dirac equation is in effect covariant with respect to Lorentz group. How this can be seen. So let us take this equation and let us multiply it from the left by gamma 0. So what we get is I gamma 0 d0 psi, and on the right hand side we obtain minus, and using this definition of this alpha we see that because sigma gamma 0 squared is 1, we obtain here just minus I gamma I di plus, and beta is gamma 0 is, so we obtain m acting on psi. Or rewriting in most elegant way, we obtain Dirac equation in the form I times gamma mu d mu minus m acting on this phi. This should be 0. And what is in fact covariant is the left-hand side of the Dirac equation, which is written in this form. For this, we will need some properties of the matrices which corresponds to this representation of the Dirac bispinors. Let us denote the corresponding matrix S lambda, and this matrix S lambda should be the transformation matrix in the left hand plus right hand spinor representation. Therefore, in block diagonal form, here should be UR lambda 0, 0, and UL lambda, since it acts on psi, which is psi R, psi L. So psi primed, the Dirac bispinor, is just this S lambda times psi. And let us now show that this matrix S lambda has nice property because it transforms the gamma matrices as vector. That means such a matrix equation gives us lambda mu alpha gamma alpha. This can be shown by direct calculation. So let us first calculate this S lambda inverse. This is just in block diagonal form right-handed representation matrix inverse, and left-handed representation matrix inverse. But we know that these inverse matrices are the same as corresponding Hermitian conjugated of the opposite-handedness matrix. So UL cross and UR cross. And now let us substitute this to this equation. So we get that this S to the -1 gamma mu S is just UL cross 0, 0, UR cross. And the gamma mu's are 0, sigma bar mu, sigma mu, and 0. And here is the S matrix, that means UR, 0, 0, and UL. And now, making the calculation, we get just, for instance, first we will multiply these matrices. So here we obtain 0, here we obtain UL cross times sigma bar mu, here we obtain UR cross times sigma mu, and 0 times this UR 0, 0, UL. And in the end, we get just 0 UL cross sigma mu bar UL and UR cross a sigma mu and UR and 0. And what we get here is the left-hand side of the transformation properties of these sigma matrices. So we know that this is just 0, lambda mu alpha, sigma bar alpha, lambda mu alpha, sigma alpha, and 0. And pulling this lambda mu in front, we obtain here just 0, sigma bar alpha, sigma alpha, and 0. This is nothing else but lambda mu alpha, gamma alpha. So this relation is satisfied. And now we are prepared to try to transform the Dirac equation in the gamma matrix form. So let us remind you that the Dirac equation looks like this. Acting psi is 0. So let us now calculate I gamma mu d primed mu minus m acting on psi primed. And let us remind you the transformation property of the psi as a field. This psi bar x primed is just this matrix S lambda times psi x, where this x primed is the Lorentz transformation of x. So let us calculate this transformed Dirac equation taken as function of x prime. So what we get? This derivative, we know that it transforms like lambda mu alpha d alpha, where d alpha is directly related to this x, minus m. And this psi prime x prime, according to our transformation property, is just psi x times s, s lambda times psi x. So let us make use of this expression and let us introduce artificially this S inverse here. But in order to have equality, we should adhere such a one in special form, and the rest is the same. Okay, so now take this in another way and calculate this. So we obtained S lambda times, and using again this relation, we see that we can transform this gamma matrix by S inverse times S, simply S, I lambda mu beta gamma beta. What remains is lambda mu alpha d alpha, and here in the second term the inverse S and S cancels, so we get here minus m psi x. But we know that this matrix and this matrix are inverse to each other. simply this lambda mu alpha is nothing else but lambda 2 minus 1 alpha mu. So contracting this mu index give us just canonical delta of alpha and beta. So alpha and beta are the same indices, and we get that this is nothing else but S lambda times I gamma alpha d alpha minus m times psi x. So we see that the left-hand side of the Dirac equation transforms covariantly in the same way as if it was Dirac bispinor. That means S lambda times the same spinor but unprimed at x. That means the Dirac equation is covariant. That means we have two interpretations. First one is the passive interpretation. Simply psi bar x primed is the solution of the Dirac equation in the primed frame, and psi x is the same solution but in unprimed inertial frame. And we see that since this S lambda is regular matrix, whenever this psi x is solution of the Dirac equation, provided I gamma times derivative minus m to psi x is 0, of course the primed observer should find the same in their primed coordinates and primed fields. As it should be. So both observers use the same Dirac equation, one unprimed, second is primed, and whenever one observer has a solution, the other observer has against a solution, and the transformation of the solution is just psi prime x prime is S lambda times psi x. We have also active interpretation. We can say, okay, so our psi prime x is, as in our active interpretation, just this S lambda times psi lambda inverse times x. This is 1. This psi x is one configuration. This psi prime x is second configuration. But provided this psi x is a solution, Dirac equation, then the new configuration psi prime x also solves Dirac equation. So this active interpretation allows us to form from one solution of the Dirac equation different solution of the Dirac equation simply using Lorentz transformations. Let us now rewrite the Dirac equation in components. So what we get is, the left-hand side is such an operator on psi, which is psi r, psi l. And using the representation of these gammas in block form, we obtain here just I sigma times delta psi L minus M, and I sigma times psi R minus M. Here will be psi R, and here will be psi L. Simply gamma matrices change L and R. They are off diagonal, while the unit matrix should be written here, doesn't change L and R. So this is the Dirac equation in the components, and we see the Dirac equation is equivalent to two equations for the spinors psi R and psi L. And just the fact that M is different from 0 makes these equations complicated in the sense that both L spinors and R spinors are mixed in these equations. In the case when m equals to 0, the left-handed equation and right-handed equation for the left-handed spinor and right-handed spinor completely decouples. You have two decoupled equations. Namely, I sigma bar times d psi l equals to 0, and I sigma times d psi r equals to 0, and these equations are called while equations. So in the case of m equals to 0, it is sometimes called also the chiral limit. The equation for left-handed spinor is completely independent of the right-hand spinor and vice versa. So for particles with m equals to 0, we can describe the particles either as left-handed spinors or right-handed spinors, and instead of Dirac equation, we can use the while equation. For instance, the neutrinos are described by left-handed spinors, and the corresponding while equation. Well, let us return for a while to the Dirac matrices, since we will need them in flows and calculation with Dirac matrices. It will be a very useful tool for calculating physical observables like model squares of scattering amplitudes and so on. So we will need some formulas for such calculations. So the first almost trivial formula is the formula that all the gamma matrices anti-commute with that matrix gamma 5. If we calculate this anti-commutator, let us remind you that gamma 5 is just such a matrix. The gamma mu's are given by this matrices and the opposite direction. So this is permutation, this is matrix which leaves the first row unchanged, but the second row is multiplied by -1. So first relation gives us just this. And here we obtain the action of this matrix from the right. So first column is unchanged, and the second column is multiplied by -1. And of course, if we add these two matrices, we get 0. In fact, this gamma 5 matrix can be also expressed in terms of the other gamma matrices as simple product of gamma 0, gamma 1, gamma 2, and gamma 3. It is, again, an easy exercise. And if we completely forgot about the concrete realization of our gamma matrices and take as the defining property of these matrices only the Dirac algebra, then such a definition of gamma 5, together with these relations, ensures that purely algebraically gamma 5 and gamma mu anti-commute. This is one observation. What about traces of gamma matrices? So according to our definition, we see that trace of any gamma mu is 0. Again, trace of gamma 5 in our concrete realization is 0. But this is not the whole story, since we can show also the trace of arbitrary odd chain of gamma matrices is again 0. The proof is simple. Let us try to rewrite this trace using special form of 1 written as gamma 5 squared inserted in this trace. This is just 1, so this is this trace. But we can take this gamma 5 and the second gamma 5 we can anti-commute to the end of this chain. According to this relation, each such anti-commutation give us a change of the sign. So we have odd number of changes of the sign. So we have here gamma mu1, gamma mu2 k plus 1, gamma 5, times -1 to 2k plus 1. This is just -1. And now we can use the cyclicity of the trace, and again, to remove this gamma 5 and move it in front of this chain. And again, we use that this is equal to 1. So we obtain that this is nothing else but minus trace times gamma mu1, gamma mu2 times gamma mu2k plus 1. So trace of any chain of odd number of gamma matrices is simply 0. What about even traces? So let us have such a chain. And now let us use this defining algebra in order to anti-commute successively this gamma 1 to the end of the chain. And then we can again use the cyclicity of the trace and relate it to the original trace. So each such commutation give us, or let us write for instance the first one. So we write simply gamma mu1, gamma mu2 as anti-commutator gamma mu1, gamma mu2 minus these gammas in different order, gamma mu2, gamma mu1. So the first step consists of 2 eta mu1, mu2, which is just this anti-commutator, times trace, which has 2k minus 2 matrices, this small trace than we started before, gamma mu3, gamma mu4, up to gamma mu2k, and minus trace when the gamma mu1 and gamma mu2 were decommuted. So gamma mu2, gamma mu1, and the rest, gamma mu3, and so on, up to gamma 2k. And we can continue anti-commuting this gamma mu2 over gamma 3, and so on. So we get, in the end, just twice gamma mu1, gamma mu2, trace gamma mu3, up to gamma mu2k, minus 2 gamma mu, and now we are commuting gamma mu1 with gamma mu3, trace gamma mu2, gamma mu4, and so on, gamma mu2k, and so on. And since this commutation is made odd times, we obtained in the same way alternating terms, and we end with trace of gamma 2, gamma mu2, gamma mu3, and so on, gamma 2k, gamma mu1. Each such operation changes the sign, and we do it 2k minus 1 times. So in the end, when gamma mu1 is at the end of the trace, we obtain here minus sign. So we can now use the cyclicity of the trace. This is nothing else but the original trace. So we can now obtain a recurrent relation for the trace of gamma mu1, gamma mu2, and so on, gamma mu2k, simply as 1/2 of the remaining terms here. That means eta mu1, mu2, trace gamma mu3, gamma mu4, and so on up to gamma 2k. Here is only 2k minus 2 matrices, and so on, minus at eta mu1, mu3, trace gamma mu2, gamma mu4, up to gamma 2k, and so on, up to eta mu1, mu2k, trace gamma mu2, up to gamma 2 mu2k minus 1. And this relation is a relation which we can use recursively. For instance, trace of unit matrix because these matrices are 4 by 4 matrices, is 4. Therefore, trace of gamma mu, according to this relation, is just eta mu times the trace of the unit matrix, and this is 4. And we can continue this game to get trace of any even chain of the gamma matrices. Okay, let me conclude this with some remarks concerning the representation of this Clifford algebra. Clifford or Dirac algebra. So, it can be proved, and you will probably do it in the seminar, that any representation of these anti-commutation relations has dimension which is larger or equal to 4. And the case when dimension is 4 corresponds to irreducible representation. That means that these matrices cannot be using appropriate coordinates in the representation space represented by block diagonal matrices. Also, so-called Pauli lemma holds, and this Pauli lemma tells us that if we have two 4-dimensional representations of this Dirac algebra and some primed gamma mu's which obey the same algebra, and the dimension of the representation is 4, then there exists non-singular matrix such that the primed gammas are just given by similarity transformation of the unprimed with this matrix S. So in fact, if we found one such a 4-dimensional representation, our representation, which is often called chiral representation, then any other representation can be obtained simply taking some non-singular matrix S and calculating such a relation. Which representation are usually used? You already know our chiral representation. You have already worked in the seminar with the Dirac representation, which is also written in such a 2-by-2 box. In this case, this gamma 0 is different from the chiral representation 1. It is simply such a matrix, which is the gamma 5 in the chiral representation. And these gamma i's are the same as in the Dirac case, only with such a arrangement. That means up to sign, it is the same as in the chiral representation. This Dirac representation is well suited for giving the Dirac equation the right physical meaning. Simply, in the chiral representation, the 2-by-2 blocks corresponds to something which has nice transformation property with respect to Lorentz group, namely to the right-handed spinor and left-handed spinor. But in this Dirac representation, these spinors are described by so-called large component, call it, for instance, phi, and the small component, let us denote chi. And you have probably made the non-relativistic limit of the Dirac equation that you have found that these large components corresponds in non-relativistic limit to the 2-component wave function corresponding to Pauli equation. And these small limits are suppressed by 1 power of mass of the particle with respect to this large component. So it vanishes in the non-relativistic limit. There exists one very interesting representation of Dirac matrices, which is called Majorana representation. In which the gamma 0 is given by 0 sigma 2 Pauli matrix, gamma 1 is given by I sigma 3, 0, 0, I sigma 3, gamma 2 is given by 0 minus sigma 2, and 0, and gamma 3 is minus I sigma 1, 0, 0, minus I sigma 1. What is interesting on this Majorana representation is that all the gamma matrices are pure imaginary. And therefore, the Dirac equation is equation with real coefficients. This I simply cancels these i's in these gamma matrices, and this Dirac equation has real coefficients. And when we have equation with real coefficients, we can found the fundamental solution of such equation real. And this has some relation to the so-called charge conjugation. Since you know that at least in ordinary quantum mechanics, the charge conjugation corresponds to something like wave function goes to wave function complex conjugated. So in this case, you can choose psi to be real, exist solution, exist real solutions, so that these solutions are then invariant with respect to such complex conjugation. Such solutions are associated with neutral particles. We will return to this later when we will show how these so-called Majorana spinors appears in the context of quantum field theory. Okay, so we have run out the time, so I think we should stop here.